Thank you for the introduction. Thank you for the invitation. Today I'm going to talk about a simple connection that we have discovered together with Yurtsever. And specifically, this connection is about this convex-concave procedure in difference of convex programming and the Frank-Wolfe algorithm in constrained optimization. So we can start with a brief description of the DC programming template. So here we have an objective function comprised of two terms, fx minus gx, and the assumption is that f and g, both of them are convex functions and they are continuously differentiable. So the objective function itself becomes non-convex, but it has this specific form of difference of convex functions. And then we also have some constraints that we allow here in the template by D. And throughout the discussion, I will focus on three different cases. First, we will start from unconstrained setting. Then we will briefly discuss what happens if we have a convex constraint, a convex set as the D. But later, we will also talk about what happens if D is non-convex of some specific structure. Basically, we'll assume that D is also defined by difference of convex functions. And maybe one important blanket assumption is throughout, we will assume that this problem has a finite solution. So f star minus g star is finite, and this will become important to discuss this equivalence, how this equivalence work. So we will start from the unconstrained setting. The starting point for the unconstrained DC programming is this simple optimization problem formulation. And the key idea behind the convex-concave procedure, it's maybe a specific case of DCA. Some of you might be familiar with the DCA algorithm. The CCCP and DCA just are different in terms of their assumptions on the differentiability of the terms. So here we will assume that f and g are differentiable. So the key idea is to use the convexity of the second term g in order to define a convex surrogate function q. Here, due to the convexity of g, if we just linearize it around some point y, this qxy for any y serves us as a global convex upper bound. And the updates in this algorithm are simply obtained by solving the surrogate optimization, the surrogate objective around the current estimation, and just iteratively solve this convex optimization problem in the hope for finding a stationary point of the original problem. One can clearly ask whether these sub-problems are well-defined, and that the answer is yes, and it comes from this original assumption that the problem has a finite solution. Since Q is an upper bound on fx minus gx, and fx minus gx we assumed that it is lower bounded, and there's always a solution for this sub-problem of the CCCP. This was the brief detour on the convex-concave procedure. Some highlights. CCCP is a specific, as we have seen, majorized minorized algorithm. That's Q surrogate objective works as the majorizer. And for the unconstrained DC program, CCCP amounts to solving this implicit equality problem. You can easily see it from the previous writing here. If you just try to solve this number 2, equation 2, if you just take with the gradient with respect to x and equate to 0, it amounts to finding this, solving this system of linear equalities. And then CCCP by construction generates a monotonically decreasing sequence. And some algorithms, numerous algorithms, can be viewed as special cases. I won't talk too much about the applications here, but the notable examples include expectation maximization or Sinkhorn's method for matrix scaling. Yes. The only difference, I think, is the differentiability assumption. I think in the literature it's called since we assume that they are continuously differentiable, yes, it's DCA. And actually, most of the equivalence here that we discuss actually also works for DCA. The only differentiability I wanted to have the differentiability to make connections with the guarantees of Frank-Wolfe. Otherwise, you can replace with subgradient and things will still hold. The only question is whether those quantities, they define stationarity or not. And we can have a quick look to the Frank-Wolfe algorithm. Here I changed the notation a little bit. Now for the Frank-Wolfe, I will denote my decision variable by omega. I deliberately chose a different notation because there will be some slack variables introduced in the original formulation of DC program to write it as a Frank-Wolfe. So we are looking at the minimization of an objective function phi. Phi is continuously differentiable over the constraint set M. I will assume M is closed and convex set. Maybe something to emphasize here, I didn't assume that it's bounded. I will come to that point later. In most of the works about the Frank-Wolfe algorithm, we focus on bounded sets. Nevertheless, we will see that it's actually not a requirement. And if you go back to the Frank and Wolfe's original work, they do not have this assumption. So the algorithm works as follows. We have the current estimate omega k. We just take a surrogate function, this time by linearizing the whole objective, phi, and solve this minimization problem. And for the solution, we do not take this as omega k plus 1, but we would just take a convex combination of this point and our current estimation to find the new estimate. And there are some different strategies, step size strategies in the literature. One common choice is the line search strategy or the greedy step size strategy. If this problem is easy to solve, one can just choose the point between these two, a point between these 2 points on this line segment, the one which minimizes the objective function. If I go back to this discussion about, oh, we didn't have the boundedness assumption, boundedness assumption is used in Frank-Wolfe for 2 main reasons. The first one is to ensure that this linear minimization oracle has a solution. But we can replace this assumption. We can replace the boundedness assumption by just explicitly saying, okay, we assume linear minimization oracle has a solution at every point in this domain. But this is a subtlety that we will rely on to write this equivalence. And the convergence guarantees of Frank-Wolfe depend on the so-called curvature constant. This definition is a copy-paste, direct writing from Martin Yagi's paper, but I find this version a bit easier to write. Equivalently, these two are equivalent formulations. So basically, for any omega omega hat in the domain, if we any omega bar chosen on the line segment between these 2 points, we should have a constant C phi that satisfies this inequality. So this is, as you can immediately see, this is very closely related to Lipschitz smoothness, but this is a bit more general. One special case, if phi is L smooth and M has a bounded diameter D, then it's very easy to see that this holds with C phi is equal to LD square. But there are some other cases. For example, if phi is concave, then you don't even need the boundedness because you can just replace C phi with 0. The existing guarantees of Frank-Wolfe, if phi is convex and C phi is bounded, the curvature is bounded, then the sequence generated by the Frank-Wolfe algorithm converges to a solution in the objective value with 1 over k plus 1 rate. And the rate becomes 1 over square root of k if we relax the convexity assumption. So if we have bounded curvature but non-convex objective, then we can say there exists an iteration tau among the first k iterations such that this gap function is bounded by 1 over square root of k, and this gap function is always non-negative by definition, and it's 0 if and only if omega tau is a stationary point, first order stationary point. So this is actually just the definition of first order stationarity. If you think about this, this comes from the normal cone of M. So one particular example, maybe less discussed, but very easy to show, is if we assume the objective is concave, and we want to look at concave minimization problem, the rate becomes 1 over k again. The proof is just very simple. It's like a toy example. In this case, actually, the line search always gives 1 as a step size due to the concavity. And the Frank-Wolfe update becomes 1 line. You can immediately choose omega k plus 1 as the minimization of the linear program, the linear approximation over this domain M. And due to the concavity of phi, you can see that gap is upper bounded by phi omega k minus phi omega k plus 1, and you can just use this inequality by, yeah, please. You can find you can evaluate the gap. Yes. So, yes, and you can basically use this as a, just by averaging, you will find that the average gap is bound by 1 over k, and obviously the best gap is smaller than or equal to the average gap. So our main result just says CCCP or DCA is equivalent to the Frank-Wolfe method applied to the epigraph reformulation of the DC program, unconstrained DC program. We basically rewrite our problem in this epigraph form and choose xt as our decision variable omega. This t minus gx is a concave objective, phi omega, and here we have a convex set. And if we write Frank-Wolfe into this new formulation, we can easily see that the linear minimization step becomes this equation 6, and that it is equivalent to, if we eliminate t again, it's equivalent to the CCCP subproblem. And the step size simply becomes eta k equal to 1 can be used because of the concavity, the line search gives always 1. So these two algorithms in this sense are the same, just applied to epigraph reformulation. And it immediately allows us to transfer the guarantees of Frank-Wolfe for the DC programming to CCCP. So if the sequence xk generated by CCCP gives us these guarantees. Fx tau minus fx minus this linearized term is bounded by 1 over k convergence rate. And this definition can be shown that this is a gap function. So this is non-negative for all x in the domain, and it's 0 if and only if this point is a first-order stationary point. So one important highlight that we have not used any assumption on Lifshitz smoothness or the boundedness of the domain, despite the fact that we are using Frank-Wolfe. And all this becomes because basically, the Frank-Wolfe inherently does not need boundedness if you have curvature, bounded curvature, and if the subproblems are well-defined. Yes. And we can quickly have a look at what happens if we have, along with the objective, if we have some convex constraints. And in this case, it's very similar, so I won't spend too much time, but we can just incorporate this set to our Frank-Wolfe objective. And if we just write down the same steps, we get to this update rule. This is actually the CCCP update rule for difference of convex programs with convex constraints. So in this case, we can also write CCCP as Frank-Wolfe. Maybe a more interesting case is this problem formulation with DC constraints. Now, DC programming has this constraint problems where not only objective is difference of convex, but the constraints are also non-convex constraints defined by difference of convex this difference of convex functions. And the extension of CCCP by Alex Small and his co-authors applies or tries to solve this problem by linearizing not only the objective, but also the constraints, or the second term in the objective and the second term in the constraints. And this becomes a convex surrogate optimization problem instead of this non-convex objective, non-convex constraint. Here we get convex objectives and convex constraints. But looking into a connection between Frank-Wolfe and this more general form of CCCP, we faced a major challenge because it seems impossible to make an immediate connection with the standard form of Frank-Wolfe. The main difficulty is that this surrogate problem, it changes the constraint set, whereas the Frank-Wolfe has a fixed constraint set. So in the Frank-Wolfe, we always keep the constraint set as it is, only linearize the objectives. But this brought the question whether actually we could extend Frank-Wolfe into more like a successive linear programming approach by also linearizing the constraints. So this is what we tried next. So we tried to come up with an extension of the Frank-Wolfe for this new template. Now we have the domain constraint M again, but along with the objective, we also have some side constraints defined by the functions phi I. And here, again, we assume M is closed and convex set, and phi and psi are the continuously differentiable functions. And we defined the extended Frank-Wolfe in this way. We do not only linearize the objective, but we also linearize the constraint functions. And again, we take a convex combination step. And the analysis was surprisingly simple and surprisingly similar to the original Frank-Wolfe analysis. There's really not much challenge coming in to do the analysis for Frank-Wolfe plus. The only challenge comes at the level of interpreting the results, because the results come a little bit different. We considered different problem settings, convex or concave, but I will start from the concave. If phi and psi, all of them are concave functions, because this is the one which actually becomes equivalent to the CCCP plus. In this case, we can ensure that the sequence generated by Frank-Wolfe plus returns an omega tau, which is feasible. So the feasibility comes from the fact that due to the concavity, this is actually a restriction of the original problem. So it always works in the restrictions of the original set. So it always remains feasible in this setting. Then the stationarity condition holds not for all points. So this condition not holds anymore for all points in M, but only for the restriction set that we have been using in the sub-problems. But it is possible to show that these restrictions are non-empty, and they also include all feasible directions. That immediately leads to this lemma that if we consider the problem template P plus that we are using with concave objectives, a feasible stationary point of problem P star can be defined in this way. So this term becomes 0, or if and only if we are looking at a stationary point of this problem, first order stationary point of this problem, and otherwise it's always non-negative. And similar results can be shown if we actually have convex functions. In this case, we used eta k equal to 2 over k plus 1 step size, because the line search becomes a little bit complicated about which functions, either in the objective or the constraints, should be used in the line search. And in this case, we can come up with guarantees similar to primal dual methods. If the functions are convex, then actual Frank-Wolfe plus is working at a relaxation instead of restriction. So the estimates are not necessarily feasible, but we have an error term that goes to 0, and when this is 0, it becomes asymptotically feasible point. Then the next proposition that we have is that we can actually write CCCP plus as Frank-Wolfe plus. And this just goes very similar to the original case of between CCCP and Frank-Wolfe. We again write, this time we introduce one extra variable for every objective and every constraint. And then we have a concave objective, some convex constraints, and some concave constraints. And if we apply Frank-Wolfe plus on this formulation, we get the CCCP plus updates, and we can immediately translate the guarantees that we derived in this case to this CCCP plus. And to my knowledge, this is the first guarantees that's shown for this algorithm, CCCP plus, for the problem template. And in summary, we recognized CCCP or DCA as a special case of Frank-Wolfe. And this realization allowed us to transfer the non-asymptotic convergence guarantees of Frank-Wolfe to CCCP for difference of convex programs. Then building on this connection, we proposed an extension of Frank-Wolfe in order to be able to transfer the guarantees of the general case of CCCP. And then we recognized CCCP plus as the special case of this extended Frank-Wolfe, and then transferred the non-asymptotic guarantees that we derived for CCCP plus. We essentially hope the connections that we uncovered here have future consequences, and then we are also investigating to transfer knowledge between the two sides. So for example, we are looking at how can we interpret array steps in the world of CCCP, or also some specific applications like expectation maximization algorithm, how it translates into the Frank-Wolfe world. And these are my references. Thank you. So I would be happy to have your questions.